Okay, so in this section of work, we're going to have a look at drainage basins. Here we go. We're going to explain the functioning of a drainage basin as an open system with inputs, outputs, transfers, and feedback loops. We've already looked at that in a previous lesson, so I would encourage you to link this PowerPoint back to your previous PowerPoint, which you should have stored in your Google Drive to understand those inputs, outputs, transfers, and feedback loops. We may need to have a discussion in class about exactly what feedback loops are, because we haven't looked at those in so much detail. One term that you will need to know is humid terrain. Hong Kong is a good example of a humid terrain. That's landscape that is dominated by water and is mainly sculpted by water. Thing for you to have a look at when considering humid terrain is that water, as it is at the top of the hill, has potential energy, and that potential energy is used to erode the river bed, and that's how we get the river valleys, if you remember, for those of you who've done GCSE geography. Of course, the object of the river, or what the river wants to achieve, is to erode all the way down to its base level. The base level is normally the sea, but depending on the river, it can also be a large lake. Here we can see the drainage basin, and it's not too difficult to understand. There's the source of the river, that's where it starts. It's the furthest point away from the mouth of the river where it enters the sea or a lake. Remember, we call that the base level. The division between the two river systems is called a watershed, or it might also be called an interfluvial. If you imagine a raindrop falling down at exactly this point here, which would be the top of the hill, in theory, it's got a 50-50 chance of going into this river, or it's got a 50% chance of flowing the other way into another river. As we said before, the whole thing, the land drained by a river and its tributaries, is called the drainage basin. If you're not sure what a tributary is, here is a tributary. It's the little rivers that go to make a large river, and where they join together, you will see that we call that a confluence. One thing that you need to understand is the concept of a stream order, and that's quite easy to understand. So we'll start off with streams here coloured in blue, and they're what we call a first order stream. When we get two first order streams joining together, it makes a second order stream. And surprise, surprise, when we get two second order, two green streams, in our case joining together, it will make a third order stream, or in this case yellow. Two third orders come together and that will make a fourth order. But you also see, just because you have a fourth order joining a third order, it doesn't change. To get to fourth order, you need two third order streams joining together. One thing that is very useful is the bifurcation ratio. I'll let you have a look at the bifurcation ratio, but the question is, why exactly are we interested in the bifurcation ratio? The important thing is that when you work out the bifurcation ratio, the higher the number, the shorter the time lag is for the river to flood. So if you have a high bifurcation number, that means your river is very likely to flood. As well as that, you need to understand discharge. Discharge is measured in cumecs, and that means cubic meters per second. So you need to work out quite simply what the cubec is. You need to work out the you need to know the speed of the river and the cross-sectional area. You can go in and have a look at these and how exactly to measure the discharge of a river in cumecs. So as we said, in a humid environment, the dominant thing that a river does is to erode and create a river valley, and this of course sculptures the entire landscape. There are some things that you need to understand that's going on in a river. There are terms for you to look up. First of all, hydraulic action. Hydraulic action is just a sheer physical force of the water smashing into the sides of here, the river. So if you imagine that 1 litre of water weighs a kilogram, if I start throwing lots and lots of water at you, you're going to know that. By itself, actually, hydraulic action doesn't cause much erosion. What really causes things to happen is the bed load. And the bed load here we can see with abrasion. The flow of the water pushes the stones along, and as they push along, they will rub against here the sides of the river. So abrasion is like a sandpaper effect. Also, you will have some attrition and solution, and I'll let you look up those terms in more detail. Here you'll see that the process of transportation, and traction is where the very large stones roll along the base of the river, and this is called bed load. Of course, over a period of time, due to a combination of attrition and abrasion and solution and hydraulic action, in fact, these stones will become smaller and smaller to such extent that we will be able to have siltation, and that's where you see the stones physically leapfrog along the riverbed. As these stones get smaller, or indeed as we increase the flow of the river, you're going to get suspension. And that's where the stones are permanently carried in the river and there's no physical contact between the stone and the riverbed. Solution, you can't actually see solution. That's because the chemicals in the rock have been dissolved in the water. Much the same way that you would dissolve sugar in a cup of tea, you can't actually see the sugar. It's one of the reasons why limestone rivers are so clear. It actually does have a lot of sediment in it, but it's dissolved in the water in the form of solution. So moving on, there's a video for you to watch here. Laminar flow and turbulence flow. There you can see laminar flow, nice straight lines. Laminar flow actually itself wouldn't be able to pick up very much sediment. It's the turbulent flow that will pick up the sediment. Of course, you're not going to have laminar flow in nature. Most of the time, the flow will be very turbulent. The more turbulent the flow, the easier it is for the river to pick up sediment. One thing you need to look at as well is the Manning's roughness coefficient. Don't get too worried about the exact equation. It's just a way of understanding how rough a river is. Really the important thing here is that, of course, the picture here is the upper course of a river. Now, because the gradient is very steep in the upper course of a river, naturally you would think that the water flow will be fast. In fact, on average, the water flow is a lot slower. That's because the river channel is very rough, and that causes friction. So the extra energy that we get from the steep slope is more than used up by overcoming this friction. So it means actually the upper course of the river is going to be very slow, which is of course not what we think. Here, the lower course of the river, there's very little gradient here, very little friction here. So even though the gradient is less, in total, the speed of the river is going to be faster. And that really is counterintuitive, both in the way that we think it and the observations we make of a river. But if you are in a lower course of the river, I would really suggest that you don't jump into it, because you will move through the river very quickly, particularly if you're in the centre of the river. Much better to see that by throwing sticks into the river, of course, if it's safe for you to do. Here is the Hjulström curve, and that helps us to understand the erosive capacity of a river. And you'll see that along the bottom here, on a log scale, so be really careful of that, on a log scale we've got the different sizes of particles, and going up the side again on the log scale we've got the velocity of the water. So not surprisingly, as the water becomes faster and faster, it can pick up larger and larger pieces of sediment. There are two lines there that you will see. One is the mean critical erosion velocity. That's the velocity that is required to pick up the material in the first place. For the smaller material, it actually takes a lot to pick up that a very high speed of water to pick up that material. But to drop that material, here we got our mean fall or settling velocity, that's much, much lower. You'll see the difference for the larger particles between the two isn't that great, and in reality it's as good as zero. So we'll talk some more in the lesson about the Hjulström curve, because there's some quite interesting things going on there. Do remember though that as the speed of the water increases, its ability to pick up the size of material increases by a factor of 3. So you double the speed of the water and you actually increase the ability, the size of rock that it can pick up by a factor of 6. I will need to check those by a factor of 3 or 6. I'm not quite sure. Together we need to check exactly what that number is. Okay, so as always, watch the other videos that are included in your YouTube playlist. Make a copy of this into your Google Drive. It's a very, very good practice to get into, that if you see any links between the separate sections of work, hyperlink this document through to the other ones in your Google Drive. And if you have any questions or comments or things that you're not too sure about, add them to your Google moderator and we'll discuss this lesson in class.